Good afternoon. Welcome to the 22nd EFRIARC Autumn Seminar. Today is the first part and is dedicated to the theme Heat Recovery in Air Handling Units and the new eco-design regulation. For about 2 hours, we are pleased to have with us a group of international guests who will give us different perspectives of this topic, which is not very consensual. I would also to emphasize that the character of and interest of the topic, as you can see from the origins of the participants who are registered today. So we have a lot of people from Portugal, obviously, but we have also from Belgium, Netherlands, Italy, India, and so on, so on, so on. Right now, we have not the total people that is in the screen, but we have a lot of people already, about 105 persons on this topic. Okay, this debate will end with this forum will end with a debate among the guests, and in which the participants could join, because we have a chat. Where is the chat? Okay, and the participants could put some questions to our guests by the chat of Zoom chat, and you can write for everybody or just for me, Luisnet. The forum is have the sponsor of a lot of brands like I'm showing right now, and I will thank to these sponsors that join with us and make possible to have this session all together. And if you want, you could also write an email from this address to further information that at the end it's not, if you don't have the time enough to chat with us, you could put your questions to the guests by this means. Finally, I will say that the moderation of this forum is the responsibility of my colleague and friend, Professor Celestino Ruivo, to whom I will turn right now the floor. And I'm wishing everyone a good forum. Professor Celestino, o palco é seu.
Okay.
And you can share your screen if you want.
Thank you, President Luis Neto. And good morning, good afternoon, good evening, depending on the place, on your location in where you are. So just now I am making a short introduction to the topic of this forum. Heat recovery in air handling units and the new eco-design regulation are important topics that have been addressed in some technical meetings of Portuguese Association EFRIARC. In spite of other similar meetings organized by other associations around the world, and in spite of numerous of studies presented in Congress related to air conditioning field and in spite of large number of published studies in literature, and in spite of the potentialities of dynamic simulation tools available nowadays, there are still few valuable published works that clearly demonstrate the technical and economical viability of using heat recovery devices. This issue seems to be simple, but in fact, it is a complex issue because, in my opinion, each case is a case. Several factors like weather, type of air conditioning, control strategy adopted for control indoor zone comfort parameters, and also air quality, number of operating hours, type and characteristics of heat recovery devices, initial and operating costs, life cycle costs should be taken in the analysis of each particular case, which difficult and time-consuming task to be done by engineers sizing and selecting air conditioning systems nowadays. The existing regulation in these fields seems to be not yet satisfactory for some agents working in this field. Thus, the technical committee of EFRIARC decided to select this topic to be discussed in this forum today. This time, foreign keynote speakers with valuable experience were invited. The first speaker is David Polverini. David Polverini is Italian, and he has a graduation in materials engineering and holds a PhD in mechanical engineering focused on design and industrial engineering methods for innovation on industrial products. His professional experience is in the fields of industry. 7 years in research and development area of domestic appliance sector and of photovoltaics, 2 years at the Joint Research Center as a scientific officer. He is a policy officer in the European Commission. He is director at General DG Internal Market, Industry, Entrepreneurship, and Small and Medium-Sized Enterprise since 2012, in charge of the implementation of the ecodesign directive and the energy labeling regulation. He is the responsible for the work on ventilation units. So I am inviting Dave for the first presentation. Dave, the floor is yours.
Ok, thank you, Celestino. Obrigado pelo seu amável convite. Infelizmente eu não falo português, então I will give my presentation in English. So I hope you can see the slides I am projecting now. So let's say I was happy for this invitation because indeed the content of this seminar is certainly very relevant for the work we are carrying out now at the level of the European Commission for what concerns this eco-design regulation on ventilation units. And I understand today your interest is mainly towards the aspects of how we would treat and we would consider heat recovery in the air handling units. First of all, before starting, just to let's say, just to check, I would start with a question, not to be replied by you now, but just for you to think. I understand many of you are manufacturers in the field of ventilation units. So I would love to ask you, how many of you are aware of this eco-design regulation 1253/2014 on ventilation units? Well, you should be aware because via this regulation, we set eco-design requirements since 2016 on all the ventilation units which are placed on the European Union market. The regulation is coupled with another regulation on the energy labeling, which is particularly targeting residential ventilation units. In fact, Regulation 1253, the one on eco-design, foresees a basic division between, a basic classification between the RVUs, the residential ventilation units, and the NRVUs, the non-residential ventilation units. The difference, which you can see shown here, is extracted from the text of the regulation. It's a difference in terms basically of maximum flow rate, which shouldn't be above 250 for residential ventilation units, unless, as you see here in the point B, the maximum flow rate is between 250 and 1000 if the manufacturer declares its intended use as being exclusively for residential ventilation application. So in essence, we classify, we differentiate the ventilation units with this definition, taking into account both the maximum flow rate and the intended use. I understand today the focus is more, the interest is more on the non-residential ventilation units. And just to mention that, as I told you, we have already an eco-design regulation in place. And for the NRVUs, for the non-residential ventilation units, we have a set of requirements. These are requirements which are compulsorily to be respected by all units. So all ventilation units placed on the European Union market shall be compliant with the requirements laid down in the regulation. Very briefly, all ventilation units, except some exceptions, shall have a heat recovery system. For these, at the next point, we regulate, and this is the main item of discussion, we regulate the minimum value of the thermal efficiency, which is basically an absolute value, which you see here differentiated on the typology of ventilation units. There are also other requirements, in particular those related to the maximum value of the internal specific fan power. And the fact, as you see towards the end, of the need of a visual signaling or alarm for related to the filter unit. So these are the current requirements already in place for non-residential ventilation units and their environmental impacts as per this regulation here. We are now in the process of reviewing this regulation. Why? Well, first of all, for a very simple reason. All eco-design regulations, by the way, I don't know how much you are acquainted with the overall functioning of the eco-design directive. I'm, let's say, given for granted, also due to the, let's say, relatively short timing for the intervention, I give it for granted that you know, in essence, what we are talking about. It's basically a regulation with product-specific measures, which tackles the environmental impacts, the aspects related to environmental impacts of products. And we typically regulate energy efficiency and, since a few years, also material efficiency aspects. So the review study, the review work started because all eco-design regulations are typically revised every 4, 5, 6 years, mainly to update the requirements, the level of stringency, definitions in light of the technological process which naturally occurs in many sectors. So we typically foresee this review work. We have started the review in January 2020, and we are tackling both the aspects related to the non-residential ventilation units and the residential ventilation units. The review work already saw a dedicated study. I have to say that a lot of, at least in my view, a lot of specific improvements, new requirements, new approaches have been proposed on on various topics, on leakages, on filters, on the ventilation performance, including humidity recovery. There has been the inclusion of more product subcategories in scope. Some of these topics are only related to the RVUs, to the residential ventilation units. Some of them are related to the NRVUs too, so the non-residential ventilation units. In terms of procedure, this is just a very detailed graph on which I will not spend so much time. It's a bit of a Gantt diagram of the typical timing. You see up to 40, 42 months that we need when having to launch a new or a revised eco-design regulation. It's a number of legal procedures which we have to accomplish. And again, I will not go into the details. This is just to mention that this is an articulated process where we value a lot the interaction and the stakeholder consultation. For what concerns the review of this ventilation units regulation, we are quite in the first part, because we have had the preparatory study. We have had, it was last February, the meeting with the Consultation Forum. The Consultation Forum is the consultative organ explicitly foreseen in the Eco-Design Directive. It is formed by member states, industry, non-governmental organizations in the field of the consumer and environment protection. And when we convene this meeting, as it was the case for the review of the ventilation units, we share before, 1 month before the meeting, the so-called working documents, which are kind of draft documents with where we show how the draft requirements, or revised requirements in this case, would look like. And we convene this meeting with the explicit interest to get the stakeholder views. So after this meeting, we collected a lot of different feedback from manufacturers, from member states, and we are now in the process of basically elaborating the various comments which have been issued. Specifically talking about NRVUs and about the energy efficiency requirements, I think it is certainly of interest to spend some time in this talk related to the potential approach we are exploring for the review of the requirement, which we have seen in the earlier slides, that we have today on the minimum thermal efficiency. We are now exploring an approach according to which there would be a modification in the way the requirement is proposed. We would basically have requirements, let's say, proposed in the standard way. So as you've seen here, as you have seen here, proposed with a minimum threshold value for the minimum thermal efficiency of the unit. So we would continue to propose this requirement in this way for those products which are, let's say, agnostic of the place of installation. So when the manufacturer does not know where the product will be installed, the requirement that will be applicable is one similar to the others, to the ones already in application. So a requirement on a fixed value. In the case, and we understand this can be typically the case for many non-residential ventilation units, in particular those of big size. In the case when the place of installation is known, we would propose to use another approach. A bit of a rationale for this. Throughout these years of implementation of the regulation of ventilation units, there has been evidence of the fact that the various climatic zones of the European Union can have a strong influence on the cost effectiveness on specifically of the requirement of the minimum thermal efficiency of NRVUs. And in fact, we got evidence from several stakeholders that in the areas typically of Southern Europe, and for example, I value today the feedback of many of you, as I understand, which are coming from this country. So many stakeholders highlighted the fact that the stringency of the requirements as they are today on the heat recovery system implies the installation of a heat recovery system, which sometimes would result in having a kind of an oversized system for the average climatic conditions. This would have an effect also in basically circumvention or non-compliance. So basically, it would seem that systems, ventilation units are still placed, in particular in warmer areas, without the properly due heat recovery system. We made an attempt to quantify the problem, even if it's obviously it's not easy because it's a matter to get evidences about non-compliances. We based on some data or an association of the sector, Eurovent, that issued some data related to the number of units. This is split throughout the whole European market, so there is not the relevance or the predominance of any specific region. And this graph here shows year by year the estimated percentage, the estimated share of ventilation units which are equipped with a heat recovery system. Having a look to this trend, one could see that indicatively, as of 2016, where indeed when we had the requirements entering into application, so the compulsory presence of the heat recovery system, as of that year, we had an increase, perhaps now under stabilization, of the units having the heat recovery system. So we could, I would say, link this to the entry into force of the application, so to the effect of the regulatory requirements. Obviously, we still see that we are at the level of 80%. So what about this 20%? Is that products which are, let's say, non-compliant? Is that products which are not in scope of the regulation, because the regulation itself has some exemptions? So this was our best guess, let's say. And we, again, with the aim to build a requirement which was kind of tailored more on the area of installation of the products, we analyzed a mathematical model which has been developed by Professor Kaup. He is the next speaker, Professor Kaup from Trier University in Germany. He elaborated a kind of a techno-economic analysis, and certainly he will be able to explain more, considering a number of parameters in the model, and as a result, there was basically given the optimal temperature efficiency of the heat recovery system. Important, as you can see here from the parameters, in this model, it is possible to consider the geographical area of installation of the unit via all these parameters, which are all location dependent. The model itself, it's basically a multilinear regression with these parameters. We developed the reasoning for, let's say, using the model for regulatory interventions. We had the first meeting in 2020 with market surveillance authorities, where we proposed the first version of this model, of this relationship. For this meeting of last February 2021, with a consultation forum, the important one where we officially discussed the draft measures with, again, member states and industry, we presented a simplified version of the heat recovery efficiency dependent on the geographical installation, basically blocking parameters such as the indoor and exhaust temperature of the building, the hours of operation per year, and leaving as only variable the outdoor winter design temperature, which again can be linked to the geographical location. I can imagine that this, seen from the eyes of, let's say, an academic, is perhaps not the optimal because it's a simplification, but we must bear in mind the usage that we do of this formula, so for regulatory purposes. And that's our current proposal, the one which we discussed in February last year. So the aim would be to basically have a new requirement on the heat recovery efficiency based and dependent on where the product would be installed, because depending on the geographical location, we would have the variation of the, obviously, of the outdoor winter design temperature. After the meeting, there was time for commenting from stakeholders. We got a lot of comments. Here you see, just as an example, some of the comments which were issued by the stakeholders, calling, for example, for alternative approaches, for example, for accepting from the requirement of having the heat recovery system for units without it in function, or when it is shown, as you can see here, that the use of the heat recovery system increases the energy use of the overall unit. So just to mention that for this requirement, as for the others we are evaluating, because we are only talking about one of the requirements under review, we've received a lot of feedback, and we are now in the process of elaborating, of reasoning, of understanding what of all this feedback can be taken into account and what can remain as per the original proposal. I don't have time to go into the detail, but please consider that we are also considering for the review of the regulation a lot of other modifications. So adjust these formulas, for example, for the internal specific fan pressure, which would be as well, as you could see for the heat recovery efficiency, would become dependent with the geographical location. We're also foreseeing minimum requirements on the filters of the non-residential ventilation units, minimum requirements on leakages, and requirements on material efficiency aspects. I close here just to recall a bit the process which we are performing. Again, we are quite, let's say, in the first part, the part of the, let's say, preparation of the act and understanding all the impacts. The second part is the more, let's say, procedural and official one. The part in which we are now is easier. And I have to say that following this meeting that we had in February, we got really a lot of valuable comments. The revised regulation is, let's say, tackles on quite a number of complex issues. Again, we have just seen a screenshot on one aspect on the proposed new approach for the heat recovery, but we could have similar discussions for each of the new requirements, and that's basically what we've done in this meeting in February. Anyway, and now again we are in the process of analyzing these comments. Probably the Commission will launch next year a further technical work, because again, we have seen that there are several technical aspects which perhaps need further analysis. I'm obviously interested and happy to get further feedback also from the participants today. Thank you.
Thank you very much, David, for your brilliant presentation. I invite participants to put questions in the chat. The questions will be answered at the end of the section. The second speaker is Mr. Christoph Kopp. He comes from Germany. Christoph is an honorary professor at the environmental campus of Birkenfeld, Trier University of Applied Sciences, for energy efficiency and heat recovery. He has a PhD in engineering and diplomas in process engineering, business engineering, and in computer science. He is a chief executive officer of OA Therm, a German manufacturer of air handling units. Christoph is also chairman of the board of the Association of Air Conditioning and Ventilation in Buildings in Germany. He's going to present a lecture for us with title European Study on Heat Recovery in Non-Residential Buildings. According to my knowledge, he wrote two interesting and valuable papers. Thus, we decide to invite Mr. Kopp to present to us his vision and some of the results of the studies he has done and published. Christoph, the floor is yours for a period of about 30 minutes.
Okay, thank you very much, Celestino. Ladies and gentlemen, warm welcome also from my side, and I'm able to do it very quick because Davide already told you a lot of the heat recovery studies we made and the results at the end, but I will show you the way how we find the results, and we did that in the collaboration with the University of Kassel. Okay, at first, some theoretic theoretics on the transmission degree or the efficiency of heat recovery, because if we would like to have a high amount of energy which we would like to use, then we have to use a countercurrent operation. That means if we talk about balanced airflows, which means that the heat transfer capacity is 1, that means the exhaust airflow is in the same range than the supply air flow, then it's very easy to define the efficiency of the heat recovery because it's NTU divided by NTU plus 1. So it's very easy to calculate. That means NTU is the number of transfer units, which is dimensionlessly value of the heat exchanger, describes the heat exchanger with this nothing else than the U value, the thermal efficiency of the heat exchanger multiplied with the surface of the heat exchanger based on the airflow, which we would like to heat up or cool down. So if we take, for example, an NTU of 1, that might be with dimensions, run coil with 8 rows, for example, 100 Pascal pressure loss, and I don't know, 10,000 cubic meters per hour, then this is a physical law that will lead us to an efficiency of the heat recovery system of 50%. Very easy. What happens if we double our effort, our NTU? If we take NTU of 2, that might be 16 rows of a round coil in your air handling unit. Unfortunately, we have then the double effort, we have double pressure losses, but unfortunately, we don't have the double of benefit. We don't have 100% efficiency. Now we will have an increase to 67% of efficiency, and so on. If we go to NTU of 3, that might be 24 rows, we will have 75% of efficiency, and 8 rows more will lead to 80%, and additional 8 rows more will lead to 83% of efficiency. So at the end, we have a plus of 400% in our effort, but only a plus of 67% in the thermal capacity. So we have a decreasing marginal benefit, but a linear increasing effort in our heat exchanger. That is the problem. And that's the reason why we have to limit the efficiency in our heat recovery system. What we did at the first point was to think about how to optimize the heat recovery system. And one point is very clear: the benefit of the heat recovery system is linked to the efficiency of the heat recovery system. So very easy, and a heat recovery system with 40% will have only half of the benefit than a heat recovery system with 80%. But unfortunately, the expenditure or the effort is linked to NTU, number of transfer units, the size of the heat recovery system and itself. And the 1D optimization is based on a constant phase area, so a constant airspeed. So we are only changing the depth of the heat exchanger to find the optimum. And how to find it? It's very easy. Possible to do it by hand. It's possible to do it with the software. Here we are using a software. And if we start with 30%, here in the first row, you see the benefit is roughly 4,400 euros, and we have to invest 700 euros, especially in electric energy, to keep the heat recovery running. and the net income, the difference cost, will be in that case 3,700 euros. If we double the efficiency, if we say, okay, now we are not taking 30%, I would like to take 60%, very easy, the benefit will be doubled, but the expenditure will not be doubled. We have 3.5 factor here in the expenditure from 700 euros roughly to 2,400. Another example, if we take 50%, you see the benefit is 7,350. And if we go to 100%, I had to do it by hand because the software stops at 75%, but at 100%, you see that the expenditure is unendlessly big. It's infinitely big. So that will produce a lot of losses. So the point of no return, the latest point where heat recovery makes no sense, is when the benefit of the heat recovery reaches the same size than the expenditure. In that example, you have a benefit at 88.9% of efficiency of roughly 13,000 euros, and you have to invest 13,000 euros. So at the end, the net income of the heat recovery would be zero. So at that point, you will have the same situation as if you don't install a heat recovery system. Then you have no benefit, no expenditure. At the end, you have zero. So it's the same situation. But that makes no sense. So a too big heat exchanger will produce losses, even like a too small heat exchanger will not reach the optimum. And here in that example, you have a clear optimum under this framework conditions, prices, etc., operating time, etc. In that example, at 67%. So here you have a maximum if you play with the depth of the heat exchanger with roughly 6,500 euros. That's one point of possibilities to optimize your heat exchanger. The second point is a multidimensional approach where you have the possibility not only to change the depth of the heat exchanger, you have two more dimensions. You have the face area, the width, and the height of the heat exchanger. But then you will change the air velocity, and it's not so easy to calculate that in an easy way. For sure, you are able to recalculate the heat exchanger 100 times with several phases and depth and so on. But here we have developed an approach to do it very easy by recalculation of U numbers, pressure losses, etc., pp. So it's a relational approach which we use. And for sure, now air velocity isn't constant, so we need an approximation equation to recalculate the U value, the thermal efficiency of our thermal transmission process. So at the end, we also have to change the pressure loss, or that's the reason why we do that. We would like to have P electric, the electric power consumption, because that is the investment to keep the heat recovery running. It will not be operated without any energy losses. We have to invest electric energy to keep the heat recovery in operation. And now here we see the 3D optimization. So we have the possibility to calculate for several velocities here, for example, for 1.8 meters per second and at 8.8 meters per second. The optimum depth of the heat recovery will be 90% of the start selection. And we see here 6,700 euros, the best benefit. And at 1.5 meters per second, you see it will increase to 7,050 euros. And the highest point we reached here, the optimum at a velocity of 1.3, 1.4 meters per second, with an efficiency roughly of 70%. And then the difference cost or the net income will be 7,100 euros. That means that we have a much higher amount of income compared to the 1D optimization. If we change only the depth of the heat exchanger, then we will see that the maximum would be 6,500 euros, for example. Yeah, so that means that we have the possibility to increase our income by a 3D optimization, and that is the best optimum of all kinds of optimums. That's the first point I would like to explain, but now my slide is hanging a little bit, and it makes no sense to increase the heat exchanger more or to decrease the airflow, because if you are going too low with the airspeed, you will have problems with your heat transfer in your heat exchanger. So there is a clear optimum. And we used all these calculations in the first study, which we presented at the Klima 2019 in Bucharest, where we took more than 3,000 real units in calculation, built units with several types of heat exchanger, with run-on coils, rotors, plate exchangers, several air flows, sizes, etc. pp. And we calculated these units, real units, for 3 destinations, 3 locations. A northern location, we calculated here, we took Helsinki as a reference. A southern part, Lisbon, you know, that's your capital city. And we did all these calculations also for Mannheim as a average or middle climate zone. And we did those calculations for 3 runtime models. We started at 2,350 hours per year, which is more or less a typical office building, up to 8,760 hours per year, which is a 24/7 operation. And for all of these, and something in the middle with 5,000 hours per year. And we have here a lot of values, but the table is not very nice to read. But here we have the same results as a graph. And you see for sure the big slope between the north and the south. In Helsinki, I think that's not academically needed, but for sure it's easy to explain and clear from the mind that in Helsinki the benefit of a heat recovery is much bigger than in the southern part, like Lisbon, for example, and Mannheim is something in between. But you see that there's not only an influence by the climatic conditions, temperatures, climate zones, you still see that there is a big influence in operation time. For example, if you have an office in Helsinki, that will have roughly more or less the same possibility of recovered heat than a hospital in Lisbon, for example. You have the same range depending on the operating time. But we don't only have to look to the winter condition, we also have to take a look to the summer conditions. And here we calculated the cooling energies related to the location and operating time. And you see there is also a vice versa slope between north and south. But if you look to the absolute numbers, you see here in Lisbon in a hospital, but there are only sensible cooling loads considered. There's no dehumidification or other issues taking into account. But you see in a hospital in Lisbon, for example, we have a possibility to recover cold in a range of 8,000 kilowatt hours. And if we look to the winter period, we see we have in the winter 80,000 kilowatts per year in the same location and the same operating time here in Lisbon. So it's even there factor 10 more relevant the winter period than the summer period. And in Helsinki, cooling loads are more or less neglectable depending to the heat recovery. And then we took our simulation tool. It's a kind of a robot where all these calculations were done automatically in a batch. And we calculated here the different results in operating with 1D, 3D optimized and status quo conditions. And here you see the results based on an economic point of view. And I think that's also clear that in Helsinki, heat recovery is for sure a good possibility to save energy and money. But if you look to the southern parts, to Lisbon, for example, you see that with the status quo selections, the heat recovery systems which were used in these cases, we produce losses, especially if we have low operating times. After 1D optimization, comparing to the status quo, after 1D optimization, we had the possibility to change the losses into winnings. Especially after 3D optimizations, we have the possibility to increase the benefits to the maximum. But you see there is still a slope between the northern and the southern areas, and there is still the influence of the operating time, but not so hard and not so terrible than with the status quo selection. But that will lead to flexible efficiencies, and that showed that a static requirement on efficiency doesn't help. So if we look here, for example, to the, there's a error. I see that the lines are a little bit misleading. The red line should be at 73%. That's the ERP requirement, as already Davide showed us, and 68% for the cyclic compound system or run-on coil. But you see that the optimized efficiencies after 1D and even after 3D are quite different. So in the northern parts, a bigger heat recovery system makes sense, and in the southern part, for sure, in Lisbon, for example, if you have an office, it makes no sense to have more than 30% of efficiency, but that was calculated with the balance limit just only on heat recovery, nothing else, no additional influence factors. But for hospitals, 60% makes also sense. In Helsinki, for example, heat recovery between 60 and 80% makes sense, for example. So what we also did was taking into account the benchmarks which were written down already in the existing regulation in the EU 1253, which was presented and published in 2014. And here we find temperature transfer rates of 85% for all kinds of systems, excepting the cyclic compound or run-on coil system with 80%, which is quite high. And if you would like to reach them, comparing to the actual standard, we see that we have to double our amount of heat exchangers. That means we have here a factor of 2. That means we have to double our effort in heat recovery to reach these values. That means we have to install not, I don't know, 16 rows, we have to install 32 rows just to achieve these requirements if they would be the next step. And we calculated also the influence of these different several conditions. It's a table, very hard to understand, but the graph shows the same, but much easier to understand. The gray column shows the status quo, the blue column, the 1D optimization, the orange column, the 3D optimization, and green is the reference condition under the sizes of the actual status quo, and the yellow column shows the reference conditions if we would use the very low velocities of the 3D optimum. 3D optimum was found roughly plus minus at 1.1 meter per second to keep the pressure loss as low as possible. And you see in Helsinki, we have still the slope between the operating times, but you see that with the reference conditions, we would produce more or less losses in offices, vice versa. 24/7 operation, we could use it, but for sure the higher amount of savings we would reach with the optimized heat recovery system, not with the standard conditions. But if you look to Lisbon, for example, you see Now it's getting hard because we will produce in all kind of situations with the reference values, with the benchmarks of the regulation losses. And for sure, the potential to recover heat is much, much lower in the southern part of Europe, Mannheim, something in between. So that we found there the optimized conditions in a range between 30% up to 77%, depending on the location and depending on the operation time. And you see, for the next step, it makes sense to use very low velocities to keep the pressure loss as low as possible, because the pressure loss costs a lot, and we need, or it makes sense to use lower velocities to keep the efficiency as high as possible. In the next step, we calculated an average unit all over Europe. We took 46 different locations from Paphos up to Turku, so from Palermo, Lisbon up to Helsinki, Oslo, etc. And you see for sure the north to south slope, and you see the influence factor of the operating time. We calculated here 2,350 up to 8,760 hours. Vice versa, the summer condition, but much smaller, but we already explained the situation, but here in a finer range with more calculations. At the end, we found difference costs which were negative in the southern parts, quite easy to understand, and which were getting higher in the northern part, especially the operating time is increasing. And also here, after 1D optimization or 3D optimization, we had the possibility to turn them in savings, in positive monetary effects, and to maximize them. But still, there is an influence from north to south. So these were the efficiencies to find these optimums. You see something between 10% and 80%. Everything is represented. So we have a wide range of efficiencies which we have to use to find the optimum. And you see that the pressure losses have to be as small as possible. Even in the northern parts, it makes sense to keep the pressure loss lower than 100 pascals, for example. And then we did some explorations about how to link the climate zone to the selecting data. And the easiest way, from our opinion, was to link the locations to the outdoor air temperature, because the outdoor air temperature, especially during the winter time, is a selecting value which is given by the customer. And you see, we took here the data from Meteonorm, that in the southern part we had temperatures roughly of 5 degrees plus, and in the northern parts, if you go to Helsinki, you see we have here a temperature of -18 degrees. So this is the blue line, and here green we have the summer temperatures. There's also a shift from north to south, and the red line is the average between the both. But at the end, we took the winter temperature because the winter mode is determine the heat recovery even in the southern parts. And it makes sense to take it because the outdoor air temperature is also a given temperature. Summer temperature is not always given by the manufacturer. So that's the reason why we took the winter temperature. And you see here a clear link between the optimums we found and the temperature for the several operation modes. And then we did also some calculations by increasing the balance limit, by taking into account the savings for heating and cooling production. So for our boilers and cooling devices, if they are getting smaller, we have savings, monetary savings and CO2 savings, which we are able to use for the heat recovery. And if we do that with the extended balance limit, we see that the shift between the efficiencies are much smaller under these circumstances. But For sure, the investment reduction is only available or usable if the boiler isn't installed or the cooling machine isn't already installed, because if it is installed, you don't have the possibility to use that savings. But it makes sense to take them into account, to give them the customer an impulse just to think about that and maybe to deal with the savings early enough to use them. So at the end, we found three influence factors: the operating time, and the temperature difference. And the temperature difference is given by the exhaust air temperatures on top and the outdoor air temperature on the bottom. And the difference is the driver of the heat recovery, as well as the operating time, same influence as you already saw. And that will lead to the optimum temperature transmission or efficiency, which is a function of all the three. And these transmission degree is determining at the end the pressure loss or the SFP value, which is nothing else than the pressure loss related or divided by the efficiency of the fan system. And what we also took into account, but only as constant values, was the investment, an average investment in euros, but we also did some calculations in CO2 emissions and the price for the emission factors and energies for heating and electricity, but also cooling. Yeah, and what we found out was the equations which Davide already showed you, the influences of operating time, as you see here. That is the axis, we have the operating time. Here we have the outdoor air temperature during the winter time, and we did these calculations for several exhaust air temperatures, and you see the plane which is given by all these three influence factors. That means, for example, here with 24 degrees extract air temperature in the southern parts, an efficiency of 45% would make sense, but in the northern part with the full operating time, we are going over 80%. And linked to the efficiency, we see also the shift of the SFP, the electric power consumption, also defined by the three influence factors. And at the end, you see if small heat recovery is required, we have small SFP factors, but if the heat recovery makes sense to be increased to maybe 80%, for sure, there's also a need for higher SFP values because the heat recovery will produce higher pressure losses than in the other cases. What we also calculated here, heat recovery only or extended balance limits with inclusive the investment costs, and you see that there is also big influence factors if you widen the balance limit also to additional investment costs, and also for the SFP, which is always a couple of pairs. On one hand, the efficiency, on the other hand, the electric power consumption. Part load operation versus full load, you see there is only a small gap or difference between part load or full load operation from the thermal point of view, but not from the SFP or the electric power consumption. You see there is a big gap between full load and part load operation. Because in part load operations, it makes sense to open the SFP value, to give higher values, because this is the value for the selecting point, but the unit is driven in part load operation, and that will lead to lower SFP, actual lower SFP consumptions, electric power consumptions during the part load operation. And at the end, we also took into account the CO2 emissions. This was the result without any CO2 emissions, because if you do the optimizations, you will find the situation that the optimums are totally different if you look to monetary aspects or geological aspects based on CO2 emissions. And to match them together, it makes sense to say, okay, if we have totally different optimums, or optimas, we take into account that CO2 has a price, and then we have the possibility to implement the CO2 emissions in our calculations. And we took here from the ETS CO2 price, which was the average in 2019 of 25 euros per ton CO2 emissions. And you see there's for sure a difference if you take into account that you will reduce the CO2 emissions with the heat recovery systems as well as the SFP. There you have also an influence by the CO2 emissions as well, as I already stated. You see that we have here a lot of possibilities, and this equation was already shown by Davide. Unfortunately, the European Commission in their draft neglected the extract air temperature. Okay, that might be a possibility to set them as a constant value. But from my point of view, I think it's a big mistake to neglect the operating time, because the operating time has the same influence factor, as you already saw, than the outdoor air temperature. So the influence factors, as already shown, operating time, exhaust air temperature, and outdoor air temperature, and also the investment and energy costs, and that will lead to the optimum of the thermal transmission degree or the efficiency as a function of all these three, and the specific fan power as a pair of couple. It's not able just to have a look only to the thermal side of the energy. We also have to take into account the link in between. So the specific fan power is following the thermal transmission degree. So at first, and as Celestino said, case is a case, that's true, but the European Commission has to define some rules to find a possible link. And here it's possible to define at first the temperature, transmission degree, and that follows, and then following the SFP value, depending on the sensible or needful or required transmission degree. And Davide, just one amendment. It would be very easy to find a gap in between the both links, because if you don't know where the place of installation is, it would be very easy to define, I don't know, minus 15 or minus 40 degrees, the lowest value to be implemented in the equations, and then you will have the requirement for the place or the location if you don't know where the unit is installed. Yeah, that was it. Thank you very much for your attention, and hopefully if you have questions, I will try my very best to answer them. Thank you very much.
Thank you, Professor Christoph. There are one question for you.
Mm-hmm.
You can see it. It is in the screen.
Yeah.
Your analysis is based on assumption that all different heat recovery systems are having same characteristics.
Mm-hmm.
As we know, different systems have different optimum points. I assume your analysis is done based on run around coils.
Mm-hmm.
It will be very interesting to see some and same analysis done both for plate heat exchangers and rotors. Have you done this?
At first, I have to say that this is not true. We made these calculations not only on run-on coils. We made those calculations, as I already showed in our study, with the more than 3,000 units. We had there 50% of plate exchanger, roughly 30% of run-on coils, and 20% of rotors. So we implemented all of them, and that's I would say an average of all. That's true, but for sure the ratio or the difference between all these systems are mainly based on the pressure loss. But if we go down to lower air speeds, we are getting the pressure losses more together, because the pressure loss is the impact of the pressure loss will be decreasing based on the lower velocities.
There is a second question from, again, from Timo. Your analysis is based on heat recovery. Isn't present regulation having its weakness, specifically that it doesn't consider cooling, including latent energy recovery, which
true.
starts to play a very important role in energy economy in South Europe? Shouldn't cooling recovery be part of your analysis?
Yeah, that's a good question for sure. But as you already said, that was really a complex job which I did. And if you look to the EU regulation, and maybe David will state that also out, that even the EU requirement up to date, the old EU regulation 2014 didn't take into account all kind of humidity changes, dehumidification or humidification. And that was the reason why we just concentrated on sensible cooling loads. And for sure, that's true. It would be very interesting to do this analysis also for dehumidification and humidification issues.
Yes, thank you. We have also questions for David, but we'll answer these questions after next presentation. Anyway, I suggested you put your questions for David and for Professor Cope in chat. We will have time to answer to more questions at the end of the session. So now next, the presentation is about the results of simulation of just a few operating scenarios of an air conditioning system with and without heat recovery in the associated dedicated outdoor air system. The presentation, the work to be presented in next communication was prepared by Professor Celestino and by Professor Francisco Hernandez Fernandez from University of Malaga. Professor Celestino Ruivo is an enthusiast and advocate of solar cooking since 2006. So it means that 80% of the energy used for cooking comes from solar. Professor Celestino has a graduation and a master and PhD on mechanical engineering of University of Coimbra, Portugal. Celestino is a professor at the Department of Mechanical Engineering of Institute of Engineering at the University of Algarve. He's also a research member of the Association for Development of Industrial Aerodynamics, ADAI, in Coimbra, Portugal. The co-author Francisco Fernandez Hernandez from Malaga University is also professor at the Energy Research Group, Department of Mechanical, Thermal and Fluids Engineering, Malaga University. He is an expert in dynamic simulation of buildings and the air conditioning systems. So the speaker will be, for next presentation, Celestino Ruivo. Thank you very much, moderator Celestino. Good afternoon, good morning, and good evening, my friends around the world. The simulation of multi-zone buildings and associating air conditioning systems is a complex task to be carried out by most of the engineers sizing the air conditioning systems. In the present work, only preliminary results of a case are presented. It is just to remove these controls. The building is a classroom located in Lisbon, and it has 28 rooms distributed by 2 floors. Each room has 41 occupants, and it is ventilated with 30 cubic meters per hour per occupant. The room is occupied from 9 a.m. to 11 p.m. The air conditioning system operates only during occupancy period, and it is switched off during weekends and post-teaching periods. The dedicated outdoor system is responsible for supplying fresh air to the different rooms. The terminal unit is responsible for controlling the indoor air temperature of the respective room. The terminal units are connected by a hydronic system to the centralized mechanical compression refrigeration system that in heating mode operates as a water heater and in cooling mode as a water cooler, chiller. In the present work, the system is simulated for 2 configurations. One configuration with the heat recover device, as we can see here, and the other configuration without the heat recover device. The heat recover device consider only transfers, only promotes sensible heat recovery, not latent. And the heat recovery device doesn't have any bypass. In this slide, you can see the expected evolutions in the different airflows at the different components of the system for both heating and cooling modes. In the cooling mode, it is represented the case where the cooling coil is dehumidifying the air, and also the case where the cooling coil is operating in dry mode as a sensible cooler. The dynamic simulation in this study was performed by Francisco, my colleague from University of Malaga. He is an expert in using Energy Plus and also Transys. But we decided to simulate the system and the building in Transys software. The dynamic simulation of the system were performed in 2 steps. Firstly, the air conditioning system was simulated for both operating modes, considering ideal system of Transys, with the main goal of finding the peak loads that are needed to determine the airflow rate and to select the terminal units and to determine the water flow rate in the hydronic circuit, to size the hydronic circuit and to select the compression refrigeration system. Then, in a second step, the real system with suitable assumptions was simulated to check the efficacy of the select system and to determine the time evolutions of the thermal capacity of terminal unities and the thermal capacity of the compression refrigeration system and the time evolutions of the electrical input power of motors of the fans, of pump and compressor. The simulations were performed by adopting a short time step of 1 minute in present study. An important simplification was adopted in present study. Instead of simulating all rooms and the associated system, an equivalent system composed of only one representative room and the associated air conditioning system was considered. Obviously, that in real context, if the thermal loads of different rooms are different, this approach would not be valid. All system should be simulated. Several assumptions were considered. I am just mentioning some of them. Airflow rate and water flow rate were assumed to be constant. Control strategy of air zone temperature implemented with a on-off fan operation of the terminal unit. Sensible heat recovery device was considered, but without bypass, as I mentioned before. A constant effectiveness value was assumed because airflow rates are constant. For the same reason, constant efficiency values were assumed for fan motors. Regarding a hydronic system, it was assumed to be a two-pipe system with only one continuous heating period and one continuous cooling period. Using the output results of the simulations given by Transys, the electrical energy consumption was evaluated in an Excel file sheet. Energy savings factor was determined to evaluate and how the use of energy recovery device is efficient or not. Being expected a reduction in the maximum electrical system, reduction in maximum electrical input power by using a heat recovery device, a power electrical reduction factor was also determined. Other indicators related with the thermal comfort were also evaluated to check the efficacy of the system. The room was simulated with a constant occupation of 41 occupants from 8 a.m. to 11 p.m. Heating mode starts at 1 November and it ends at 30 April. The remaining period of the year corresponds to the cooling mode. This means that the system can be in operation only in 3,915 hours. It works only in 45% of the time. Regarding the weather data, the file for Lisbon, also used by Energy Plus, was used in the simulations. In this table, you can see some information about input data associated with the internal room loads. And also data about clothing and metabolic rate of the occupants. And also information about set points values for the indoor temperature that were considered in cooling mode and also in heating mode. It is also shown the values for the relative humidity. We know that the system does not control the relative humidity of each room, but when simulating the ideal system, we consider these values for the relative humidity. Regarding the mechanical compression refrigeration system, it can operate in cooling mode as a water cooler and heating mode as a water heater. And here you can see how, observe how the COP in each mode is influenced by the outdoor conditions, by the dry bulb temperature in cooling mode, and by the water that is being water temperature that is being produced. And here the same information regarding the heating mode. These data were obtained from the technical catalog of the manufacturer, and these data were implemented in Transys and considered in the simulation. Two scenarios were considered. Scenario SC1 and scenario SC2. In scenario SC1, low pressure drop values in different airflows and in water flow were considered. When the heat recovery device is not used, we have considered 200 Pascal in the fresh air flow and 150 Pascal in the exhaust airflow in the dedicated outdoor air system. We have considered 400 Pascal and 350 Pascal in the dedicated outdoor air system, respectively, in fresh air and exhaust air when adopting a heat recovery device. We have considered 220 Pascal for the total pressure drop of airflow crossing the fan coil, and 50 Pascal for the pressure drop in the water flow in the hydronic circuit. So this is the scenario SC1, low pressure drop values. In the second scenario, high pressure drop values in different airflows and in water flows were considered. 400, 300, 800 Pascal and 700 Pascal when simulating the heat recovery device, and 389 Pascal for the pressure drop in the fan coil, for the airflow crossing the fan coil, and 100 kilopascal for the pressure drop of the water flow. Regarding the efficiency of the pump, of the fans, and the effectiveness of the heat recovery device, the values adopted, the adopted value for each of these variables is 60% for scenario SC1 and for scenario SC2. In this table, we present output performance results of the ideal system simulated in the first step for the reference configuration without heat recovery and for the configuration with the recover device. With the thermal capacity values of the cooling coil and of the heating coil, the airflow rate of 0.7542 kilograms per second and 0.502 kilograms per second were determined for reference configuration and when using the heat recover device, which corresponds to an important reduction of 32% in the airflow rate. In water flow rate, we determined 0.61 kilograms per second and 0.514 kilograms per second, respectively, for the case without heat recover device and for the case using heat recover device. So it corresponds to have a reduction on 16% in the water flow rate when using a configuration with the heat recover device. In this table, you can see a lot of numbers, but first we can see that the airflow rate associated to the ventilation and to the exhaust air doesn't depend on the configuration and doesn't depend on the scenario. But we can see that from these results of the simulation of the real system, the input electrical power values for the fan motors are greater when using the heat recover device and are also higher in case of scenario SC2 as expected. The consumption of electrical energy associated to these fans also vary in the same manner as expected. Regarding the fan coil, the impact of using a heat recover device in the dedicated outdoor air system leads to non-negligible reduction on peak thermal capacity and also on power and energy consumption of the respective fan motor of the fan coil. The same impact is verified in case of the pump of the hydronic circuit. Regarding the machine used for cooling water and for heating water, when using a heat recover device, its maximum electrical input power and its electrical energy consumption are smaller when adopting a heat recover device. In spite of the mentioned positive impacts of using a heat recover device, the higher energy electrical consumption values associated with the operation of the two fans of the dedicated outdoor air system, it has a negative impact in energy savings when heat recover device is used. Using a heat recover device in present case corresponds to an additional energy consumption of 80% in case of the scenario 1, so the scenario with a low pressure drop, and an additional consumption of energy of about 20% in case of scenario 2, the case with a higher pressure drops. The overall negative impact is mainly due to the negative impact observed in cooling mode. The use of the heat recover device has a small positive impact in the reduction of the peak load, as you can see here, but only 4% in case of scenario 1 and 6% in case of scenario 2. Room indicators were also evaluated. The obtained results show, for example, that the use of the energy heat recovery produce an important increasing in the discomfort of the occupants due to ambient overheating. Following the standard ISO 7730, 59% of the time of the heating period, we are observing that the occupants are dissatisfied with the ambient. This also is observed by the fact that when using the heat recovery device, the indoor temperature is 90% of the time of the heating period with 2 degrees Celsius above the set point. It means if the set point is 20 degrees, it means that in this heating period, the air temperature of the zone is in between 21 and 22 in 90% of the heating period. Regarding humidity, the results indicate that the values are relatively high during small periods. The operation of this system will be critical, not in this case of Lisbon, but it will be critical in cases, in terms of humidity, in cases where the weather is very humid. And for concluding my communication, I will say that the selection of air conditioning system based only on winter and summer design peak conditions is questionable. Simulation by a trained expert taking into account weather data along the year, real performance of equipment, and use of the building is crucial. And researchers like me should make studies focused on finding practical solutions with acceptable efficacy and with better efficiency. Compulsory use of heat recovery devices imposed by regulation seems to be questionable. So, in my opinion, each case is always a case. Thank you. So now, you have time for questions. Time for questions.
We don't have any questions now.
No questions?
But we have some questions from the previous guest. Okay. I will share my screen. So
okay, thank you.
So I think you are seeing this.
Okay, so questions to David.
Yep.
Or questions or comments. So the first one is other factors should also be taken in consideration, namely indoor heating and cooling needs and application. To evaluate an ERS, an energy simulation must be made for each case. In many applications and climates, the installations of as ERS increase energy use, which is contrary to the proposal of the ecodesign directive. David, can you give any comment to this question or comment of Carlos Lisboa?
Thanks for the question, the comment. Well, what I presented here, this so-called scenario B or second approach, goes exactly towards the direction of trying to consider more, as you concluded in your slides, that each case is a case, meaning that I see, quite frankly, too complex to be treated under the eco-design directive. So far, we only have one example, very specific for the transformers, to systematically introduce the needs of an assessment showing the, I suppose, techno and environmental, the economic and environmental feasibility of the case. I would rather keep, as shown today, the approach with a normative proposal, obviously modified in a way, tailored in a way to take more into account the local specificities. If I may, I also saw another comment, if I may reply, concerning the relevance of still including the other aspects in this formula we have proposed, for example, of the operating hours, something that we have simplified. Just to highlight, because I couldn't have time to elaborate on this during my presentation, but I think it's anyhow important to mention it, to highlight the fact that we are kind of not constraining our analysis, but whenever we are proposing a different, a new, a revised regulatory approach, we always need to take into account a multitude of different factors. One certainly is the technical and scientific relevance of the method. So we started from the method developed by Mr. Cow, and then we operated some simplifications. We did this because there are then other reasons for including these. I mean, for doing the simplification, which is basically the verifiability. These are requirements which should be checked by the national market surveillance authorities, and obviously they should be given tools which are not too complex, which can rely on, let's say, kind of straightforward information. So we always have the tension between these very different aspects, and that's why we operated this simplification. So to cut the long story short, I would still see, after the comments we got over the past months, overall, I would be inclined to keep this approach we have been proposing, probably with some improvements. For example, the one mentioned by Mr. Kaup related to systematically including the installations where the place is not known with the lowest value of temperature. These are kind of simplifications, but overall, I would still see the case for continuing. And again, an important stakeholder in this discussion, alongside the manufacturers, and today we have mostly manufacturers, is also the market surveillance authorities, which should help us in ensuring that whatever we propose can be verified.
Thank you, David. So I guess you replied to both the questions of Carlos Lisboa. Neto, is there any more question?
Celestino, are
Yes.
you seeing my screen?
Yes.
The question made by Timo to David.
Yeah, on this one, in the document we circulated in February concerning the draft revised regulation, we made an effort in adding the consideration in the factoring in the calculation of the recovery efficiency related to the humidity. parts, because so far in the current regulation, it recovery efficiency is calculated assuming dry conditions. Here it is something where, quite frankly, we have received a lot of comments, because obviously whenever we introduce a new element, it means that there are assumptions made, and we have seen that specifically with this aspect of humidity, I could see quite different views among stakeholders. So we are not still with a finalized view on this. We've made an attempt, but I'm not sure if this will be retained until the end.
Okay.
We have more time for one or two questions. No?
Okay, but I don't have any questions.
So if we don't have any question, but if people have questions after the meeting, they can also contact us, the Secretariado of EFRIARC, or myself, or the speakers, if they need additional information or to clarify any topic that was not clear addressed here. So if you don't have more questions, so it's I thank you again, the speakers to be here in this meeting, and it's time to conclude the section, to close the section, this forum, and now.
Okay, I ask to Carlos Lisboa to say something to close this session. Okay.
Can you hear me?
Yes.
Yes.
Okay. So first of all, I would like just to add information to all that EFRIARC participated in the stakeholder meetings regarding the eco-design regulation review, and our experience was that the process was extremely transparent and open to different views. Our opinion was heard and published immediately in the website, and it's important that everybody understands that European regulations should be participated and discussed by all affected parties, and our experience is that the procedure actually works very well. Then I would like to, in the name of EFRIARC, thank all the speakers for their availability and knowledge sharing with all of us. Also, a final thank to the sponsors that make possible the implementation of this kind of sessions, and hope that the session was useful to all participants, and hope to see you in future sessions. Good afternoon to all.
And that's all. Thanks, Carlos. That's all for today. See you next time.
See you. Bye-bye.
Bye. Thank you.